operations with complex numbers is not much different than operations with polynomials. You're going to distribute collect like terms like you learned in 8th grade. You're going to FOIL like you learned in 9th grade or 8th grade. The only thing really here that you have to worry about is how to do problem C. Part A is simple. Just distribute the negative and collect like terms. You add the real parts, you add the imaginary parts. So all you have to do, and this is on the My Open Math. These are gimme problems. And I have a section on the test Friday where it's just this stuff. All you got to do is simplify complex numbers. Really gimme stuff. So this one, all you have to do in part A. So part A, you just distribute the negative. So you'll have 1 minus 2i. Actually, you can drop the parentheses at this point. So you have 1 minus 2i, and then distribute this negative. And so you have minus 3 minus 4i, and you end up with negative 2 minus 6i. This is your complex number. Remember, a complex number is of the form a plus bi, where a is the real part, and bi is the imaginary part.
Did you find your Apple Pencil?
I did. I'm so thankful it was underneath the cushion where my nieces played with the iPad.
Oh my gosh.
I know. I was so glad. I was nervous. Okay. Anyways.
How much does a pen like that cost?
120. All right, here we go. So that's A plus BI. So mine was 120. Mine's the new version.
Oh.
Yours is the cheaper
Yeah, I
one.
don't know. We have the older
I have the new one. All right, so negative 2 minus 6i. Negative 2 minus 6i. This is the real part. This is the imaginary part. Okay? I've had it for 2 years. It works really well. Okay? All right, that's it. That's all you did. The next one, all you do is FOIL. But you do got to remember some patterns. Let's review the pattern. Let's see if you remember the pattern from yesterday. Who can tell me the pattern from memory yesterday? If you don't have it memorized from Friday, you're going to miss about 4 problems. I, negative 1, negative I, and 1. You better have that memorized by Friday.
Okay.
I, negative 1, negative I, 1. Because if you ever run into I squared or I to the third or I to the fourth, you do have to simplify those down. Okay, if you see I to the 75th or I to the 35th or I to the 9th, you got to simplify those down to one of these 4 things. So let's pay attention. Okay, I, you're okay with. You're okay with I, negative I, 1, and negative 1. But anything beyond that, you have to simplify it down. All right, this one we're going to FOIL. So letter B, we're going to FOIL. We get a 3. Okay, first, outer, inner, last. We get a plus 4i. You treat i's like terms. They're just... All I is a variable that represents the square root of a negative. I'm going to say it again. I is a variable that represents the square root of a negative. Okay, then you have minus 6i. And then you're going to have minus 8i squared. Oh, got an I squared. You're going to have to replace it. What can we replace I squared with? Every time we see I squared, we can replace it with negative 1. If you need more I, Saley, we can go get you some. Okay, so we're going to have 3. I can combine these like terms because imaginary numbers are like terms. So I have negative 2i. And then it'll be this I squared is a negative 1. So you're going to have a negative 8 times a negative 1. If you want to go ahead and make that plus 8, you can. You don't have to show any work there. You can just make that plus 8. A lot of people just change this to plus 8. You see what I'm saying? Okay. You're picking up what I'm putting down. So we got 3 minus 2i plus 8. So we're going to have 11 minus 2i. There's the complex number, 11 minus 2i. The real part is 11. The imaginary part is the negative 2i. Pretty straightforward. Now, this is the part that most people don't remember how to do. This would have been on the ACT. Okay? Some are like, oh, gosh, I probably missed this one. Yeah, you probably did if you don't remember this. Because this requires what you call a conjugate. You remembered?
No, I definitely didn't.
Okay. Did anybody remember what you do here? What you do to get rid of, because an imaginary number is like a root. It represents the square root of a negative. You can't have roots where? You can't have a root in the denominator. Everybody say it. You can't have a root where? And an imaginary number is really a root. It's the root of a negative. Remember, poke the I out. Okay? So here's how you would usually just multiply the top and bottom by I. Don't write this down. But it don't work. Because the problem is there's a binomial on the bottom. So if you multiply the bottom by I, you're going to get 3I minus 4I squared. So you're able to get rid of the I here because I squared is what? But the problem is you reintroduce the I there. So what we do is use what's called a conjugate. And this is really important because we're going to talk about the conjugate, the complex conjugate pairs theorem. What is a conjugate? You need to learn this right now. This is the last thing I'm teaching today before we start factoring these things down. And we're going to do what's called the complex conjugate theorem. It's so valuable. All right, you ready? If you have a complex number a plus bi, its conjugate is the same binomial. Okay, it's called the conjugate's pairs theorem. The conjugate, all right, that's how you spell conjugate, C-O-N-J-A-G-A-T-E, conjugate. I spelled it wrong. It's a U. What am I smoking? Right when I wrote it, I was like, I spelled that wrong. I'm embarrassed. Conjugate. How about spell it right?
Come on, Marsh, you got this.
I got it. Could not get that U in the middle there. Conjugate. Okay? The conjugate. A conjugate is the exact same binomial. You just change the sign in between them. So if you have a plus bi, what would the conjugate of a plus bi be? A minus bi. Now here's what's special about conjugates. When you FOIL them, when you take two complex numbers that are conjugates of each other, where all you do is change the sign in between them, watch what happens. You don't have to write this. You can if you want. What's a times a?
A squared.
You get a perfect square. That's going to get rid of any root that you have. So you'll get rid of any kind of root that was there because you get a perfect square. A times negative bi would be negative abi. Would you agree with that? And then on the middle, you get a positive abi. What happens to the abis? See ya. Because they're like terms. They're going to cancel. They're opposite of each other. And then you get minus b squared, I squared. So you get a perfect square. And not only do you get rid of, you get a perfect square to get rid of any square roots, you also get an I squared, and I squared becomes what? So you end up with a squared plus b squared. In college, and you are in college, they actually require you to know that a minus bi times a plus bi always gives you a squared plus b squared. It gives you a squared plus b squared. Let me demonstrate. If I have 2 minus I, what is the conjugate of 2 minus I? 2 plus I. Watch what happens when you FOIL them. I'm going to FOIL it the long way one time, just one more time, just to show you what happens. If you FOIL this, what's 2 times 2?
4.
What's the outers give you?
2i.
What's the inners give you?
So negative 2i.
What's the last give you?
I squared. So negative
Middle terms what?
cancel.
When you multiply conjugates, what always happens to the middle terms? What always happens to the middle terms? So you end up with just a squared, 2 times 2 is a squared, and you end up with b squared, which is I times I. What's I squared? So you end up with 4 plus 1, because I squared is a negative 1, so you have minus a minus, which is plus 1. There's the a squared plus b squared. The answer is 5. You will always get a real number when you're done. So here's what you learn to do. If you're really good at it, you start to say, oh my gosh, this is awesome. All right, let's go 3 root 2 minus I. What's the conjugate of 3 root 2 minus I? 3 root 2 plus I. And if you're really good, you just cheat. You don't even do the whole FOIL. You just say the middles are always going to what? So you just go, let's just multiply the firsts and the lasts. And what should happen is, because they're perfect squares, you'll get rid of any root. And you also get rid of I because it becomes I squared. And I squared is what, everybody? All right, what's 3 root 2 times 3 root 2? 9 times 2. Because root 2 times root 2, I told you 2 weeks ago, is what?
2.
Anytime you multiply a root by itself, it cancels the root. Or, as Brody said a couple weeks ago, it's root 4. But root 4 is really just 2. Okay? So a root times a root cancels itself. 3 times 3 is 9. Root 2 times root 2 is 2. And then you get minus I squared. What does I squared become? -1, so you get 18 plus 1, which is what? 19. You'll always get a real number. So real quick for me, why don't you do this? Take this. Take 2 root 2 plus 4i, multiply it by its conjugate. Go. Fast as you can. All right, the conjugate would be 2 root 2 minus 4i. Agreed? Since you have conjugates, you only have to multiply the first and the what? Last. So what's 2 root 2 times 2 root 2? All right, 2 root 2 times 2 root 2 will be 8. Did everybody get 8? Did everybody get 2 root 2 times 2 root 2 is 8?
Yeah.
Okay. Minus 16i squared. What is 16i squared really? It really just becomes a plus 16, does it not? Because I squared is -1, that'll just change it to plus 16. So the answer is what? The answer is 24. Multiplying conjugates. It's so easy. All right, so with that said, how do you get rid of an I in the denominator when it's a binomial? Use the conjugate. What is the conjugate of 3 minus 4i? We're going to multiply by 3 plus 4i. But whatever we do to the bottom, we must do to the what? So, yes, is one of these on your test? For sure. So that's the only one I'm really worried about you getting is part C. I'm not worried about the rest. The rest are easy. Part A is just distribute like time terms. Part B is just FOIL. Part C, learn how to use the conjugate. It's easy. Now the bottom, since they're conjugates, do you have to FOIL the whole thing on bottom? What can you do if they're conjugates? Just do the what? First and the, what's 3 times 3? 9. What's 4i times 4i? So that'll be minus 16i squared, which is actually going to become a what? Because I told you it always becomes a squared plus b squared. Now the top, you don't have a choice. What do you have to do on top? You got to FOIL. They're not conjugates. So you have to do what you did in part B. So FOIL at top for me. Keithan, what would the top be FOILed?
Foil the top. Oh, 1 times your 3,
Okay, good.
and then you'll do your 1 times your 4i,
Good.
then -2i times 3,
Negative 6i, good.
then -2i times 4, -8i, or -8i squared.
There you go. So then the top ends up, you can simplify the top and you can simplify the bottom. The bottom's going to end up being 9 plus 16, agreed? Because I squared is what, everybody? -1. It just changes the signs. The top, you can make this a plus 8. So we're going to have 3 minus 2i plus 8, because again, that I squared is going to change the sign. So end up with 11 minus 2i over 25. And you're going to hate me now. You got to see, can you reduce this? Well, can anything go into everything? Don't worry about the I. Can any number go into all the numbers?
No.
Then it's simplified. You can't reduce it. What if that would have been, well, never mind. I couldn't have changed one. All right, now let me go to part D. Part D, I love this with 9th graders because they never pay attention to little details. I'm telling you, what did I say you always poke out first?
The I.
Poke the eyes. If you do not poke the eyes out first, you're going to think a negative times a negative is a what?
Positive.
But you're going to be wrong. Because you have to poke the eyes out first. The imaginary number has to come out first. So I'm going to have I root 3 times I root 12. Now, you're going to get I times I is what? So the I squared is actually going to make the answer what? See, if you would have multiplied a negative times a negative, you would have gotten a positive, and your answer would have been wrong because you would have missed the negative. So you got to poke the what out first, everybody. Sound effect for me first. What do you do? Boop, boop, boop. Poke those eyes out, baby. Okay? All right, I squared. What's root 3 times root 12? I don't know. I don't even want to. Maybe you put 36. Maybe you don't, but you got to simplify square root of 36. What's square root of 36? 6. And then what's I squared? Negative 6. Why is it negative 6? Because I squared is a negative 1 and the square root of 36 is 6. So you have a negative 1 times 6. If you would have multiplied that negative times a negative first, what would have happened to those negatives? And then you would have gotten 6 instead of negative 6. So poke the what out first. All right. Now, this one's different though. Do you see the difference?
You multiply them first.
You can multiply them first because they're both underneath the same root. So now you can follow, please excuse my dear Aunt Sally. So this one you can multiply. That's the square root of 36, so that gives you what? Do you see the difference between D and E? D is 2 separate roots where you have to poke the i's out first, then multiply them. E is 1 root where you can go ahead and simplify underneath the root and then simplify. All right, F looks complicated, but it's not. Look at this. X minus this. X minus this. All right, it looks like these are conjugates, don't they? Does that look like conjugates right here to you? Interesting. Let's see what happens when I FOIL two things with x minus the conjugate pairs. Okay, let's see what happens. So I've got 1 plus 2i, 1 minus 2i, which is going to lead to our conjugate pairs theorem. It's wild what happens here. It's really quite simple. Okay, let's FOIL it though, because we don't know what's going to happen yet. What's x times x?
X.
Does everybody agree?
Yep.
All right, now let's do the outers. We're going to have minus 1 minus 2i x. You agree with that? I didn't do anything really. I just combined them with multiplication. I have an x times this negative. We know there's a negative, so that's where the negative comes from. I have this 1 minus 2i. That's where that is. And then I just put the x behind it. You okay with that? All right. Now let's do it with this one. Is it going to be the same thing again?
Yeah.
Minus 1 minus 2i x. And then we're going to have a negative times a negative is a what? And we're going to have 1 plus 2i times 1 minus 2i. So we're going to have this times this now for the last part. All right, let's simplify this and see what happens if I multiply this all out. All right? So we're going to have to do a little work here. Okay, I'm going to have to distribute the x here. Distribute the x here. Or I could say, are these not like terms? Are those like terms?
Mm-hmm.
So couldn't I just say there's 2 of them?
Yeah.
So minus 2x, 1 minus 2i. Because there's 2 of them, right? I might as well just put the x out in front. Are you okay with me moving the x from the back to the front?
Yeah.
All right. Now, are these conjugates?
Yep.
What do you get when you multiply conjugates? You only need to multiply the first and the what? So it'll be 1 times 1. And then it's going to be a minus 4i squared, which is going to end up being 1 plus 4. What's 1 plus 4? 5. Got an x squared. And then we're going to have a minus, ready? Here we go. Minus a 2x. Minus a what? 4ix. There it is. Kind of weird looking, isn't it? Wild. Okay? Any questions on how to do all that? Pretty straightforward. Oh, wait. Why did we not get that? Oh, wait. We could not added those. I screwed up. I totally screwed up. This should have canceled out. Do you see what I did wrong? Do you might see what I did wrong? Call me out on it.
Weren't you supposed to have one of the 1 minus 2ix is positive?
Yes. I got to stop me before I get that far. Let me go back through it. What's x times x? Everybody look. What's x times x? Because if you can see the mistake, you're going to be like, oh, yeah, duh. X times x is x squared. Does everybody agree with that? I'm gonna erase all this just so you can re-see it here. All right, do you see it? X times x is x squared. X times negative 1 minus 2i, that's correct, right?
Yep.
All right, so we did the first and the outers, correct? Now let's go to the inners. It's supposed to be a minus x, but it's supposed to be a 1 what? It's supposed to be a plus there. Do you see what I did wrong?
Yep.
All right. So, only mistake, but that's actually going to make it work out even nicer. Because, and the reason I stopped myself is because I was like, wait a second, if you take conjugate pairs, this is going to lead to our conjugate pairs theorem. It should end up being real. So we're going to get x squared, watch this. Now, we can't combine these then, can we? So now we can distribute the x. So we're going to have minus x. All right, what's a negative times a negative? Plus 2ix. Because I had two negatives there. Agreed?
Yep.
All right. Then we're going to have minus x. And then minus 2ix. And this we did correct. What was that when we multiplied that out? It was going to be, it ended up being plus 1 minus 4i squared, which is really 1 plus 4, which is what? 5. Now, what happens now magical that should have happened? The 2ix's cancel. So we end up with x squared minus 2x plus 5. Which, if you set that equal to 0, did quadratic formula. Here's the magic I want you to see. Okay, are you ready? This leads to what's called the conjugate pairs theorem. Let's solve this with quadratic formula right now. Review the quadratic formula with me. If I take that original problem, x squared minus 2x plus 5, and I set that equal to 0, can you find the factors of 5 that add up to give you negative 2? Can I find the factors of 5 that add up to give me negative 2?
I think so.
Really, what are they?
Probably like 2 and a 3.
Negative.
2 times 3 doesn't give you 5.
Give or take a negative.
Oh, wait.
2 times 3 is 6. Can you find the factors of 5 that add up to give you 2?
I always think it's the other way.
Yeah. Can you find the factors of 5 that add up to give you 2? So you'd be required to use what? You're crazy. Not on an x squared, you would not. You're required to use quadratic formula. So, Keithan, what is the quadratic formula? What is the quadratic formula?
Be negative b plus or minus root. I forgot the rest. Yeah.
You better not forget it for Friday.
I'd have to get the song cooking. Yeah, he does.
Okay. All right, negative b, plus or minus squared, b squared minus 4ac, b squared minus 4ac, all over 2a. Okay? Not knowing the quadratic formula alone will cause you to not pass the test Friday. Because it'll be used on about 6 problems. All right, here we go. Negative b, what's negative b? 2. Plus or minus the square root of? What's negative 2 squared? 4. Minus 4 times 1 times 5 over 2 times 1. Are we good with that? All right, are you ready? Here we go. 2 plus or minus the square root. What's 4 minus 20? Negative 16 over 2. Wonder what we're cooking up here. What's the square root of negative 16? Poke the I out first. 4i. Is there something that'll divide everything? Is there something that'll divide everything? 2. A 2 will divide everything, agreed?
Yeah.
So a 2 will go into this once, a 2 will go into this twice, a 2 will go into this once. We end up with 1 plus or minus 2i. Look, conjugate pairs. 1 plus 2i, 1 minus 2i. Look, if you write it back in factored form, remember you always do the opposite. X minus 1 plus 2i, x minus 1 minus 2i. There it is. There's my 2 zeros. And if you wrote it back in factored form, it'd be x minus 1 plus 2i and x minus 1 minus 2i. And we just multiplied that out to see that it gave us x squared minus 2x plus 5. Here's the thing about imaginary numbers. They always show up in conjugate pairs. So if you've got the plus 1, you automatically have the what? So if I tell you 1 plus 2i is a root, what is also automatically a root? 1 minus 2i. If I tell you negative 3 plus 4i is a root, what is automatically also a root? Negative 3 minus 4i.
How come you only teach us
You only change the middle sign
Why?
because that's the conjugate. Because it's A minus B times A plus B is what causes the middle terms to cancel. You only change the sign in the middle. Did I change the sign of the first? I only changed the sign in the middle. A plus BI, A minus BI. She asked a really good question. Okay, follow me here. I want to see if you get it because I'm leading right to the conjugate pairs theorem. What is, if I give you 2 plus I, what automatically shows up as another root? 2 minus I is also another root. If I give you negative 3 plus I, what also shows up as another root? Negative 3 minus I. Now I'm really going to blow you away. If I give you 2I, what also shows up as another root? Negative 2I. Because it's really 0 plus 2I, 0 minus 2I. Is that not true? It's really 0 plus 2I, 0 minus 2I. Because remember, that just means there's no real part. Okay, if I give you negative 4I, what automatically shows up as another root? 4I. If I give you 5 plus 2I, what automatically shows up as another root? 5 minus 2I. Are you getting it? If I give you negative 6I, what shows up as another root? Imaginary numbers always show up as conjugate pairs. So that's going to lead me to the conjugate pairs theorem and the fundamental theorem of algebra, which is the last thing I have to go over. So the conjugate, A plus BI, is the number A minus BI. Now, they usually use, if they want to say conjugate, there is a shortcut for writing the word conjugate. Are you ready? If they don't want to write the word conjugate, I can just say A plus BI with a bar above it. That means conjugate. So, are you ready? If I give you 3 plus 2I, what does that mean? It means the conjugate of 3 plus 2I. What is it? That's it. That means just tell me what the conjugate is. I'm not going to write what is the conjugate of this. I'm going to put the complex number with a bar above it, and you need to know that means what's the conjugate. So if I put, ready? If I put bar 3 minus 2I, what does that mean? 3 plus 2I. What's the conjugate? If I put bar 5I, what does that mean? Negative 5I. If I put bar 3 plus root 2, what does that mean? 3 minus root 2. Okay, do a couple more. If I put bar 2 minus I, what does that mean? 2 plus I. I'm going to go until you get it. If I put bar negative 3 minus I, what does that mean? Negative 3 plus I. If I put bar negative 6I, what does that mean? 6I. If I put bar 7 plus root 2, what does that mean? 7 minus root 2. Now I'm going to throw a trick question at you. Are you ready? I'm going to throw a trick question at you. What's the only part we changed in the complex number? What's the only part we change in the complex number? The sign in the middle. So it's really the imaginary part that gets switched. So what if I only give you the real part? You don't change anything. Because it's really like 6 plus 0I. So it'd be 6 minus 0I. If there's no I, do you need to put it? So if I just do the conjugate of just a real number, like a real number, like the conjugate of 7, it's just 7. The conjugate of negative 8 is just negative 8. That's a trick question. Conjugate of a real number is just the real number. You don't change it. You only change the sign in the middle of the complex number. So you only change the plus BI or the plus the root. Okay? So that leads to properties of complex conjugates. Let Z and W be complex numbers. Okay? Let Z and W be complex numbers. All right? What's double conjugate of Z? If Z is a complex number, you ready? A plus BI. What would the conjugate of Z be? A minus BI. And what would the double conjugate then be? You'd be back to A plus BI. So if you do a double conjugate, won't that just get you back to the original complex number? So if you do a conjugate twice, that gets you back to the original. Double conjugate gets you back to the original. Don't really gonna use this. If it just comes up on the My Open Math is all. I'm probably not putting it on the test. Now.
No, put it on the test. Yeah, you definitely gotta put it on the test.
You like that? Double?
Yeah.
Okay, fine. So if I go double bar 3 plus 4i, what is everybody putting? 3 plus 4i. Is that okay?
Yeah.
If I took 1 bar 3 plus 4i, what are you putting? All right. Okay.
Watch me forget that.
Yeah, don't forget that. All right, now here, this is kind of cool. If you add two conjugates of two different complex numbers, let's say z is a plus bi. Let's say w is d plus ci. So they can be different. All right, there's two different complex numbers. Do you agree? All right, you have a plus bi and d plus ci. So if I take the conjugate of z, what would the conjugate of z be?
A minus bi,
A minus bi. Do you agree? What would the conjugate of w be?
d minus ci.
All right? True? So if I add these together, let's add them together. What are you going to get?
A d
You're going to get a plus d plus minus bi minus ci. Do you agree? If I add this plus this, is that all you're going to get? So it's saying you can find the conjugate of each and then add them, or can you add them first and then find the conjugate? Let's add them together first. What would that give you?
a plus d
A plus d, that's the real part.
plus bi plus ci.
Bi plus what?
ci.
Ci. All right, now if you wanted, so that's z plus w, agreed?
Yeah.
Is this z plus w? What would be bar z plus w?
A plus d
A plus d
minus
minus,
bi
now distribute the negative. Did I give you the same thing? So does it matter if you do the conjugates first and then add them, or add them first and do the conjugates?
It doesn't matter.
All it's saying is you can do the conjugate first, then add them, or you can add them and then do the conjugate. Most people like to do the conjugate first and then add them. It's just a property. These are just properties. There's nothing special about them. They're just properties. Probably not going to have. I will do this one on the test for you. Probably not going to do this one. Okay? This is the same thing. It says you can do the conjugates first and then multiply them, or you can multiply them and do the what? Whatever. This says you can do the conjugate first, then raise it to a power, or you can do the power first and then do the conjugate. So these are the properties just saying you can add, multiply, raise it to a power. Now, which one did I not do? Which one did I not say you could do? Division or subtraction doesn't work with conjugates. You can't divide first, then do the conjugate, and it's the same thing as do the conjugate and then divide. It doesn't work for division and subtraction. It only works for addition and what? Multiplication.
First, then, if it was
Huh?
if it was division or subtraction, which one do you have to do first?
You have to follow the orders of operations then. You just have to do what it says in the order. You can't. So if it says z bar divided by w bar, you got to do z bar first, then w bar, and then divide. You can't divide first and then do the conjugate.
So is a bar like a parentheses thing, or that is how that comes first?
It kind of acts like an operation, yeah, like a parentheses. But it means conjugate, that's all it means. And then the last thing, if z is a real number, what did we say? You guys said you wanted this. If z is a real number, the trick question, if I have bars 6, it's just what? When it's a real number, it doesn't matter because there's no imaginary part to switch the sign in the middle. All right, that's it. We already proved that. All right, can polynomials be... All right, here we go. Yes, finally. Okay, to the last part. And then tomorrow, all I'm going to do the entire class period is practice problems. Is just do homework problems. Okay, here we go. Fundamental theorem of algebra, FTA. Everybody say it, FTA. It's pretty fat without a PH. Okay? All right, FTA. All right? Fundamental theorem of algebra. Suppose f is a polynomial function with complex number coefficients. So that means the coefficients could be complex numbers. They don't have to just be real numbers. They could be complex numbers. So it could have imaginary coefficients. You could have roots in the coefficient. Of degree n greater than or equal to 1. So it needs to at least be what? Needs to at least be linear. It's got to at least be linear. So we're throwing horizontal lines out. So it's got to at least be a line. Okay, but if we go to x squared, then it's a parabola. If we go to x to the third, then it's a cubic. If we go to x to the fourth, then it's a quartic. If we go to x to the fifth, then it's a quintic. X to the sixth, then it's an x to the sixth. X to the seventh, I don't have any more names. It goes, ready? Constant is horizontal line. X to the first is linear. X squared is what? Quadratic is a parabola. What's x to the third? Cubic, which most of you think of a disco curve. X to the fourth, does anybody know what x to the fourth is called? I don't require you to know the names, but they're kind of nice. 4 quarts in a gallon. What's x to the fourth called? Quartic. 4 quarts in a gallon. Quartic. And x to the fifth? It's called quintic. Does anybody know why it's called quintic? What's Spanish for 15?
Quince.
Quince. It comes from that suffix in Spanish. Okay? For 5. Yep.
Why don't
Yeah.
we call it a pentant?
That's for polygons. I always thought that too when I was in high school, but they got different names. Now, I don't require you to know the names, but if you know the names, it might be extra credit for you. Oh, people perked up all of a sudden.
How
Oh
far?
my
Like,
goodness.
how far?
Actually,
How
we
many?
know what.
Okay?
Yeah, how
All the
many
way down to
things
10
are
or up?
Nope,
to
just
10?
a 5.
Just a
What?
5.
Yep, 0 is constant. 0 is constant.
Okay, hold on.
X to the 0 power is constant. Not cos. Constant, that's a horizontal line. X to the first power is what? Linear. What's x squared?
Quadratic.
Quadratic, which is a parabola, but I need you to know that, I don't want you to know what the graph looks like. I want you to know the name, quadratic.
You should add if we know what it looks like. Is more
Oh, we
extra
get-
credit.
What's our x to the third? Cubic, which is disco curve. What's x to the fourth?
Quartic.
Quartic, 4 quarts in a gallon. I don't know how you can't remember cubic, because x to the third is cubed, x cubed.
What does a
Cubic.
quartic look like?
They don't call it a.
It's just like
Don't
a
they just
flat
get,
round.
like-
There's x to the fourth.
Don't they just get like,
No, x to the fourth. Well, it's really flat.
It would- Yeah.
It gets really flat at the bottom. It's like a parabola, but it gets flat. But if you go x to the fourth, like plus x cubed plus 3x squared, then you start to warp the middle. So that sucker can start going up and down like that. So what you do is you warp the middle, and if you add more terms in there. What's x to the fifth?
Quintic.
X to the fifth is quintic.
Wait, so if x to the third is cubic, why don't they call it like squadriatic then for x squared?
What?
Like, because you say x squared, but you don't say x squad or like a squadriatic.
All right, here's why. A quadrilateral is a four-sided shape, and the area of a quadrilateral is length times width and ends up being square units. So that's why it's squared.
Okay. That makes sense.
Yeah, it comes a little bit from geometry. The names aren't always consistent, but they kind of use some things from other things that we use it with to kind of relate it. So it's, yeah, I get it's not perfect. But quad means x squared, quadratic.
wait, more, so if the x squared.
You would think quad is 4, but it's not. What now?
If the quadratic's like,
X squared,
like length and height and stuff,
length times width.
and yeah, and the cubic's length times width times height,
That's x to the third.
then what is x to the fourth?
X to the fourth, you would need a fourth dimension, which it's your mind can't visualize it. Maybe it's time, maybe it's something else, I don't know. String theory requires 24 dimensions or something like that. All right, now we get to the complex factorization theorem. So once you find the roots, we know that when I find the roots, what page is this on?
I was on page like
290? The complex factorization theorem says this. By the way, if n is greater than 1, then f has at least one complex 0. So what we're saying, the fundamental theorem of algebra says that if you have complex coefficients of degree n greater than or equal to 1, so it's at least linear or down, then you're going to have at least one complex 0, which means there's going to be one 0 that has an imaginary, or it's going to have a root in it. It's going to either be irrational or it's going to have a root. So that's why you need this, to be able to find those really complicated ones that you can't use factoring for. Okay? All right, complex factorization theorem says this. Suppose f is a polynomial function with complex number of coefficients. If the degree of f is n, and n is greater than or equal to 1, which means it's at least what?
Linear.
It's at least linear. Then f has it exactly n complex zeros. So whatever the degree is, that's how many zeros it has to have, including complex numbers. So if it's degree 6, how many zeros are there? 6, including imaginary numbers. If it's degree 7, how many zeros are there? Including imaginary numbers and irrational solutions. Now, it doesn't necessarily have to cross that x-axis that many times because will imaginary solutions cross the x-axis? So remember when we had degree 6, we could bend a bunch of times. So we could go 1, 2, 3, 4, and that looks like degree 4, but then degree 6, it would bend again. And these up here wouldn't cross the x-axis, so it crosses 4 times. So it seems like it's degree 4, but there's some more bending that goes on because those two are imaginary. So it still adds up to 6 solutions. There's still 6 solutions. It's just 4 of them are real and 2 of them are not real. We're going to show you how to find the not real now. Now, if you do have those distinct zeros, okay, and I know this gets really technical. It gets really heady. If you have Z1, 1 0, a second 0, all the way up to how many ever zeros you're allowed, according to the degree. All right, these are the distinct zeros of F with multiplicities 1, 2, and K, respectively. So the multiplicities can be whatever power you raise it to, remember? Like if it's to the second power, that would be multiplicity 2. If it was to the first power, that would be multiplicity 1. If it's to the third power, that would be multiplicity 3. So you could also include multiplicities to count up to your degree. So everything has to add up to your degree, including complex numbers and multiplicities. Okay? So, are you ready? Here we go. We're going to try and factor this completely and find all the zeros, including complex numbers. Factor using the complex factorization theorem. So after you get the zeros, I want you to have it in factored form. So you got to find all the zeros, and then you got to factor it. Now, I haven't mentioned this, but this does come up, and I don't know why it's put later. We've already said this. The conjugate pairs theorem says this. If f is a polynomial function with real number coefficients and z is a 0, then what is also a 0?
The conjugate.
Conjugate. So the conjugate pairs theorem. So this is why it's interesting with 6. It doesn't necessarily mean plus or minus 6, because what's the conjugate of 6? 6. That doesn't mean plus or minus. But when you have the conjugate of 3i, it does mean what? Negative 3i. So you get plus or minus 3i. So if you have 2 plus 3i, what do you also get? 2 minus 3i. If you get root 3, you also get what? Negative root 3. Okay? What's wrong?
Morse, what happens if it's like doubled? Double conjugated?
Remember, it's the same.
It just is, but even if it's a positive?
Yeah, that'll never change. Double conjugate 6 is always, that's a 6. You can do triple conjugate, quadruple conjugate. That's 6 no matter what.
Got it.
Okay? Yeah. You like that? That'd be a fun one. So, that leads to being able to do this. I'm just going to get started. I'm not going to do Cauchy bound. I'm not going to do Descartes rule signs. I'm going to do what's really practical. Just do the flipping rational root theorem. All right, what's the P? What's the P here? All right, you better pay attention now. I don't know what that page number is on. Page what?
290.
Page 290. Everybody go to page 290. I'm doing that one. P. So my P is 1. What's my Q?
12.
Oh, dang it. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. All right, so what are all the P over Qs?
1
Plus or minus 1,
plus or minus 1 half,
plus or minus 1 half,
plus or minus 1 third,
plus or minus 1 fourth, plus
1 6,
or minus 1 sixth, and plus or minus what?
1 12.
All right, there's everything that could work right there. All right, what are we going to, so that's the only things we try. Guess what? If I give it to you on the test and you don't have a calculator, it's going to work fast, okay? Hey, you confident, Haley? If I'm going to give you no calculator, Stella,
Stella.
Greta, called her sister. I had flashbacks of her sister sitting in this class. Okay, Greta, if all I have to do is know that if I don't give you a calculator, it's going to be one of these P over Qs. and it's going to happen quick. It's probably not going to be a fraction. And if it is a fraction, it's going to be an early one. I'm not going to make you go deep into this. All right, let's try 1. You ready? 12, negative 20, 19, negative 6, negative 2, 1. This is how good it should look when you get good at this. Are you ready? Race me. I'm going to give you a head start.
So right now, PQ's right.
So,
Try 1. Let's pray it works. All right, I got a 12, I got a 12, I got a negative 8, I got a negative 8, I got an 11, I got an 11, I got a 5,
it works.
I got a 10, I got an
Oh, wait, no, it doesn't.
8, and I got an 8. Did it work? Doesn't work. So now what should we try?
I did some dumb work.
Negative 1. I have the liberty, I can erase. You asked if to write it down again.
Oh, I just erased it.
Okay, cool. I got a 12. I got a negative 12. I got a negative 32. I got a 32. I've got a 41. I've got a negative. This is looking too big, isn't it?
Yeah,
If you get to a point where you're like, I don't think this is going to work, should you just keep going?
no.
No. You should stop and say, that one doesn't work. Now what are we going to try? Let's try a half. I bet a half's going to work. 12. I told you I'm not going to get deep into this. Half of 12.
6.
If you can't figure that out, I have no hope for you. All right, negative 14. That gives you negative 7. That gives you 12. That gives you 6. Ooh, I got a 0. I love zeros. Love it when I get zeros. Love it. Okay, got 0. Got negative 2. That gives me now. Oh my gosh, I got a remainder of what?
0.
What should you do if you find one that works?
Do it again.
Try it again. Do it again. Because this means that might have multiplicity 2. Now, we've took it from x to the 5th. What are we down to so far? We're down to x to the 4th. We got to get it down to x squared so we can use quadratic formula.
Oh.
All right, here we
If it
go.
works again, then you do it again.
We got to keep going until we can either factor it or use quadratic formula.
Well,
Here we
let's
go.
say This works
Can we just
again,
use
would you do it
quadratic?
again?
Let's see. You can't use quadratic formula until you get it down to x squared. Or something that's a trinomial where its power half the power constant. Okay? All right, drop the 12. That's why we got to practice lots of problems tomorrow. You need exposure. Okay, I got a 6. I got a negative 8. I got a negative 4. I got an 8. I got a 4. I got a 4. I got, oh. Guess what?
It worked.
It worked twice.
So do you do it again?
Try it again. It could work 3 times. Now we're down to x to the 3rd. Man, let's pray it works again, because if it is, we're down to x squared and quadratic formula will finish it for us. All right, what do we got? Does it work again? I bet it does. 12, 6, negative 2, negative 1, 7. No. Dadgummit.
So do we?
All right, we've got it to x to the 3rd.
We gotta find another thing. Do you gotta like say?
All right, here's what I would do at this point. If it's really this hard, I would try negative 1/2 real quick, just to see. Let's see if negative 1/2 works.
Wait, can you use it with that?
Yeah, use it with this.
Oh.
Yep, just go right from where you left off. Drop a 12, we get a negative 6. What do we get? I get a positive 7, that gives me 15. Does that look like it's gonna work?
No.
All right, I don't wanna bother doing the rest, so here's what I'm gonna do. I'm gonna assume at this point, Mr. Morris has made it to where it factors. What worked twice?
1/2.
So you got x minus 1/2 multiplicity what?
2.
You good with that? Now I've got this left over.
It was negative 1/3.
Oh, negative 1/3 worked?
That's
Yeah,
next
That's
one.
what it says in
Oh, you cheaters.
the, right below it.
Hold on, before I do it, let's see, 12, I've got x minus 1/2, because remember, you got to do the opposite, right? Squared, agreed? So it's 12x to the 3rd minus 8x squared plus 8x plus 4. It is possible that this works with factor by grouping. All right. Now, if you don't want to factor by grouping, then you have to keep hammering out synthetic division. But you could try it real quick to see if it factors by grouping. If it doesn't, then you got to go back to synthetic division. Let's see. Does it factor by grouping? Can I factor anything out of the first 2? let me finish this. Can I factor anything out of the first two?
4x.
4x squared, what will that leave me with? 3x minus 2. Okay. Can you factor anything out of this? That'll leave me with 2x plus 1. If these aren't the same, then factoring by grouping doesn't work. So guess what? You're going back to what? You're going back to synthetic division and hammering it out until you find something. Which, everybody, I want you to finish it. What worked?
Negative 1/3.
Do negative 1/3. That'll get you down to a squared. And then you finish it with what?
Quadratic formula?
And then you write it back in factored form. And that's where I'm going to pick up tomorrow and do tons of practice.
So we should just do that.